You're looking at a sleek machine sitting quietly on a launch pad. But the second you push the throttle, electricity surges from the battery. Those 4 rotors wake up, and it lifts into the air. Once it's in the air, the drone looks steady, but it's actually doing a lot of work to stay there. Gravity is constantly trying to pull that heavy frame back to the ground, and the drone has to work every millisecond to stay level. It stays airborne because its onboard computers and high-speed motors are fighting an invisible war against the planet's physical laws. These rules were first mapped out by Sir Isaac Newton. He defined the strict laws of motion that every flying machine, from a paper plane to a high-tech drone, has to follow. To understand how this works, you have to develop a kind of X-ray vision. You need to see the 4 invisible forces constantly wrestling with each other in the sky. Take a look at this red arrow pointing down. This represents our first force, weight. Gravity is always pulling the physical mass of the drone, the frame, the motors, and that heavy battery, straight down toward the Earth. To stay up, the drone needs a defensive reaction. That's the blue arrow pointing up, which we call lift. As the blades spin, they slice through the air and create an upward push. Notice how the red and blue arrows are now the exact same length. They're locked in a perfect tug-of-war. When the upward push of lift exactly matches the downward pull of weight, the drone stays perfectly still in midair. So to climb higher, the engineer just has to make the motor spin faster, creating enough extra lift to overcome the drone's weight. To move forward, the drone tilts its nose down. This directs some of that motor power backward, creating a new forward-pushing force called thrust, shown here by the green arrow. But as the drone moves, it runs into a new challenge. Even though we can't see it, air acts like a fluid that resists anything trying to move through it. You can see this resistance as the yellow wavy line pushing against the front of the drone. We call this friction drag. Watch how the yellow line grows longer as the drone speeds up. The harder the green thrust arrow pushes forward, the harder this invisible wall of air pushes back. This means every move a drone makes is a calculated choice to unbalance these forces just enough to push through the atmosphere. You can actually see these aerodynamic forces in action without any electronics at all. All you need is a rectangular strip of paper and a paperclip. If you fold the paper into a simple helicopter and drop it, gravity immediately pulls it straight down. That's the force of weight at work. But as the paper falls, the air rushes up and hits those angled paper flaps. Because the flaps are folded in opposite directions, the air pushes them into a rapid spin. That spinning motion turns the paper flaps into tiny wings. They start catching the air and generating just enough upward lift to slow the fall and steady the flight. A high-tech drone uses the same principle. Its propellers are designed to catch the air and use it to conquer the constant pull of gravity. So here is the complete picture. Every second a drone is in flight, it is managing weight, lift, thrust, and drag all at the same time. For an engineer, success means understanding how to control this high-speed mathematical balancing act. But there's a hidden complication. When a motor spins a heavy propeller clockwise, the body of the drone naturally wants to twist in the opposite direction. If you had 4 motors all spinning the same way, the entire drone would spin wildly out of control the moment it left the ground. Solving this twisting problem requires a brilliant mechanical workaround, and discovering that secret will be the primary objective of your next mission briefing.